Welcome PCS members and friends to our PCS IBS seminar. Today we are very happy to host and have with us, although only virtually, but nevertheless, we are very excited to have Dr. Thorsten Wahl from University of Cambridge, UK. And our scientific host today is Zung, who will introduce our speaker. Please, Zung.
So thanks, Thorsten, for accepting our invitation, and thanks everyone for coming. So today we are very happy to have Dr. Thorsten from Cambridge University. He did his PhD in Max Planck Institute of Quantum Optics under the supervision of Professor Sirac, the director of the institute. After the PhD, he went to Oxford and worked with Professor Steve Simon as a Marie Curie Fellowship. And then after Oxford, he moved to Cambridge, so on the big university, to work as a researcher in the Department of Applied Math and Physics. Today, he will give a talk on neural network application in Euler insulator. And Thorsten is very well known over the world for his pioneer in Tensor network, and I hope that we can learn a lot of interesting physics today. Thank you. Let's welcome the speaker.
Yeah, thank you. Thank you so much for the kind introduction, also for inviting me to give this talk. I will now try to share my slides. So you can see that?
Yeah.
Yes.
Okay. So yeah, I will talk about a project I did recently in collaboration with people from Cambridge. So most importantly, my supervisor, Robert Jan Slager, and also with some Adrian from Stockholm. Yeah, and this talk is about exactly representing Euler insulators, so a specific type of topological systems with tensor networks. So I want to explain, first of all, why tensor networks are useful, or why they've become so important, and then also why they're struggling to actually capture a lot of topological systems, but nevertheless can represent Euler topological systems exactly. So, okay. So tensor networks are, I mean, they're normally represented via these graphs of connected balls or boxes. So this is just a graphical representation of telling people what a structure for tensor network is. And the important thing about tensor networks is that they have a number of parameters, which are the entries of those tensors. And that number of parameters has to grow only polynomially in the system size in order to keep the error of the approximation fixed. So tensor networks are a variational ansatz that for lots of relevant physical systems overcomes the exponential scaling problem of the quantum many-body problem and reduces it to something that's only polynomially complex, so which can in principle be done on a classical computer. And that's why they have become so popular. So overall tensor network states are a non-perturbative approach. They're not related to the non-interacting limit, even though I will be talking a lot about non-interacting systems in this presentation, but in general, they don't require being connected to any non-interacting limit. They're generally non-perturbative, and they also don't suffer from the sign problem. So they can handle fermionic systems in the same way as bosonic systems. One also doesn't have to change the codes too much for tensor networks. And as a result, tensor network states have already had a number of big successes. On the analytical side, they have enabled the complete classification of topological phases in one dimension. And in two dimensions, they have enabled people to classify symmetry-protected topological phases. From a numerical perspective, they have now reached machine precision in one dimension. So at least for one-dimensional gapped Hamiltonians, one can represent ground states with tensor network states basically exactly on a conventional computer. And in two dimensions, they have now started beating alternative methods. So I think the most prominent example is that in certain parameter regimes of the two-dimensional Hubbard model, tensor network states have now given rise to the most accurate results. So in this talk, I will be mostly considering topological systems. So topological systems are relevant, like from a technological perspective, because they might enable us to encode quantum information sort of securely, protected from noise from the environment, so basically quantum memories, and at the same time also enable protected quantum information processing, with the ultimate goal of obviously building a universal quantum computer. And topological systems might also be relevant for enhanced or speed up of classical information processing. So what I'm showing here is, for example, the toric code. So this is a relevant example of a quantum memory. And on the right-hand side, the fractional quantum Hall effect, which is probably the most studied effect in condensed matter physics. So the fractional quantum Hall effect is has a chiral topological feature. So this is what you can see in the bottom left corner. So for the fractional quantum Hall effect, one has like one chiral edge mode propagating around the edge of the system, and the same for an integer quantum Hall effect. And in the right bottom corner, you see helical edge modes, where there are two counter-propagating gapless modes, which is the quantum spin Hall effect, which might enable much faster classical information processing. So there's, on the one hand, technological interest in topological systems, but obviously also for physicists, they're just exciting because they're exotic phases of matter with non-abelian excitations, which you couldn't have like in genuine free systems. So I mean, as a result, there's basically a zoo of different topological phases, and it's very hard to classify all of these topological phases. But at least in a limit of no interactions, so free fermionic systems, complete classification has been carried out. So this is what I'm showing here. This is called the Alt-Land-Zillenbauer classification, which was sort of found by Schneider et al. And also Kitaev in 2008 and 2009. And so what you can see here is the different symmetry classes that you have for as a basically dependent on anti-unitary symmetries. So this is free fermionic systems which can have time reversal symmetry, particle Hall symmetry, or none of them, and they can time reverse symmetry, particle Hall symmetry. The operators can square to +1 or -1. As a result, there are 9 classes. And if there is no time reversal symmetry, no particle Hall symmetry, you can, or you might not have a chiral symmetry. So overall, it's 10 classes which are labeled from A to A1. And for all of these classes, it has been characterized what the different topological phases are. So topological phase in that case means it's impossible to connect a Hamiltonian in that topological phase with a Hamiltonian in a different topological phase without either breaking the symmetry or closing the gap in the system. So these are phases that are protected to perturbations. And as you can see, then the classes that one gets as a function of the dimension of the system, so this is the last 3 columns, are either just one trivial topological phase, which is labeled 0, or we can have 2 different topological phases with a topological phase and a trivial phase, which is labeled Z2, or we can have a topological phases labeled by an integer Z. So this is the complete classification of topological phases in 1, 2, and 3 dimensions for free fermionic systems. And free fermionic systems can always be diagonalized efficiently by other methods. But just to benchmark what tensor networks are able to do, people have also tried to apply tensor networks to these sorts of systems. So this is something I did a lot in my PhD. And it turned out tensor network states are actually struggling a lot to represent the 2- and 3-dimensional topological phases. So there's a rigorous proof by Nick Reed, which shows that in the free fermionic limit, so if you work with free fermionic tensor network states, then if you restrict them to have short-range correlations, so basically to mimic gapped systems, then they can only represent the one-dimensional topological labels. So only in one dimension they can represent the topological phases properly. In higher dimensions, numerics will always give rise to a long-range decaying correlation, so the tensor networks don't capture the physics exactly of these systems. So only the labels that are marked in red can be represented exactly by tensor networks. And this is proven rigorously, but in this talk, I want to go beyond the outline syndrome classification. Yes.
Sorry, we have a question.
Yes. Yes. Sorry, I should have said, please ask me questions at any time during the talk. Yes. Go ahead.
Just a curiosity about in general, the tensor network. You said this is the non-perturbative approach. So the validity of this tensor network, is there any limitation? For example, in any energy window, this tensor network is available?
Yes, so I haven't really talked about the restrictions of tensor network states. So tensor network states have been shown to represent ground states of local gapped Hamiltonians efficiently. So as long as you have a Hamiltonian in any dimension and it is local, which means either it has strict short-range interactions or it has exponentially decaying interaction terms, and it has a gap, then you can represent it with a tensor network state efficiently, which means that for the tensor network state, the quantum many-body problem is only polynomially complex. So you only need to increase the number of parameters polynomially in the tensor network state, and also the calculation time, the memory, etc. is all just polynomial in the system size if the Hamiltonian is local and it has a gap. Does that answer?
Can you calculate the excited states that with this?
Yes, very good question. So in general, tensor network states are made for ground states. So you cannot, in general, represent excited eigenstates with tensor networks. There are some cases where tensor network states also enable us to do that. So if there's an isolated branch of excitations like quasi-particles, then tensor network states can do that. And you basically have to modify the tensor network a little bit. So basically create something that's like a quasi-particle and then take the translation invariant superposition of that. So there's a way of doing it if there's an isolated branch of excitations, but if there's like a band of excitations, then tensor network states in general cannot do that.
Okay, thank you.
Okay, very welcome. Yeah, and please interrupt me at any time if you have more questions. I'm also becoming very technical right from the beginning here. I'm aware. So tensor network. So and this is basically now a way of benchmarking tensor networks. So can they capture the non-interacting topological phases that we can represent very well with non-interacting band theory, or do they have problems? And it turns out they have problems if we are in 2 and 3 dimensions, but they can capture the one-dimensional topological phases. But now I want to move beyond that tenfold classification and go to systems which are protected by crystalline symmetries. So tenfold classes, they're protected by anti-unitary symmetries like time reversal and particle symmetry, but they're also topological phases, still non-interacting, which are protected by crystalline symmetries. And this is also something that has been completely classified with many more topological labels. So it's in the bottom row here, you see the topological labels as a function of the wallpaper symmetry group. So this is the classification without anti-unitary symmetry. So that's basically class A. But one can also combine it with anti-unitary symmetries. And I just want to consider one particular combination because it's experimentally so relevant. And that is the combination of inversion symmetry with time reversal, so PT symmetry. So this is relevant in many experiments. And for that particular symmetry, so a combination of a crystalline and an anti-unitary symmetry, there is a topological label, that's the Euler number, and that exists both in 2 and 3 dimensions. The only restriction is that you basically have 2 occupied bands and 1 empty band. So the 2 bands need to be well isolated from the other band. And in that case, you can define a topological label. So this is quite different to the previous classification where was always a class for just a single band. You could use just a single band and calculate a topological index. But in that case, one always needs to have like these 2 occupied bands to define a topological label. But again, one has an integer topological label, the Euler number, that exists in both 2 and 3 dimensions. So now it's ideally suited for testing the tensor networks on them, because as I said, tensor networks struggle to capture these topological labels in higher dimensions. So this is the outline of my talk. So in the second part, I want to introduce specifically these Euler systems in a bit more detail. And in the third part, mention why tensor network state works so well and what their restrictions are. And in the fourth part, I will apply tensor networks to describe these Euler systems. And this is all like a rigorous description. So in that case, I'm not using the tensor networks numerically. I basically will show you a model like an experimentally relevant, very simple model whose ground state is exactly captured by the tensor network. So the tensor network captures the Euler number and all the correlations, etc., exactly. And in the fifth part, I will talk about some special features that this model has as a result of being captured by a tensor network. And in the sixth part, I will take advantage of the fact that we have a tensor network to make the whole thing interacting. Because Euler systems so far have only been considered in the non-interacting limit, and now we can use the tensor networks basically as a toy model to write down interacting Hamiltonians, which are in the Euler class. So the Euler systems, so as I said earlier, the prerequisites are PT symmetry, which means that the Bloch bands can be made real, so they can all be gauged to be real throughout the Briorine zone. And as I said, we need at least we need exactly 2 occupied bands, which is isolated from 1 empty band. And I will just be considering 2-dimensional systems here. And then we, for example, have a band structure, as you can see in the middle. And it's important that the 2 occupied bands, they actually have to touch each other. And then in certain cases, they give rise to a non-trivial Euler number, so to this integer that I was talking about, which can be calculated by integrating basically over the derivative of the Bloch wave functions. And the integrand here is called the Euler curvature.
Question.
Yes.
Why do the 2 bands have to touch each other? Comment briefly. You said it.
Yeah, yeah, no, it's a very good question. The reason is because the Euler number doesn't exist for just a single band. So the Euler, so something I didn't go into, the classification that gives rise to the Euler number is multiband topology. So in the past, people just wondered about what happens if we have a number of occupied bands and a number of empty bands, and there's a gap in between. But then later on, people also started classifying systems where you have multi gaps. So we just don't have one gap, but you have multiple gaps in the system which separate bunches of bands. And for the Euler system, it's very important that the bunch of bands that is separated consists at least of 2 bands. So you cannot get so if you just have a single band and you calculate the Euler number, I mean, you can see it depends on 2 bands. So a single band would be topologically trivial under PT symmetry. You need at least 2 bands. And I think if you had 3 bands, then it would again be a Z2 classification. So it depends a lot on how many bands you group together for PT symmetry. And since you have to group the bands together, they necessarily have to touch. So I mean, the bands must not be separated by a gap, because otherwise the thing would be topologically trivial under that symmetry.
Thank you. So here you are considering spinless bands.
Say it again.
Are you considering simple systems or spinless systems?
Simple systems or?
Or spinless.
Spinless. I see. That's a good question. So it doesn't. It doesn't really depend on whether it has a spin or not. It just depends on how many bands you have. So I mean, there might. I don't know if there are also spin systems which have an Euler number, but in principle it should be possible. So the only requirement is that you have basically 2 bands which are isolated from the rest, and you could probably also write down spin models with that feature. So we'll be mostly considering Kagome lattices here, which have which are spinless, so spinless fermions, because in that case you have 3 bands, because the unit cell of the Kagome lattice has 3 sites. And if you introduce the spin, you would have 6 bands. So then you would have to write down a model where, again, 2 bands are isolated from the rest. But in principle, that should be possible.
I think there's an example for that in the twist graphene.
Okay.
You have the same Euler insulator, but spin, but you have also valley, and by like combination of spin and valley, you have like multiple churn insulator and multiple Euler insulator at the same time. So I think that example with the spin food and Euler insulator happen in real experiment.
Okay, that's pretty cool. So it definitely does exist.
So the group in like Benedict appear on anywhere, but the group in Sweden by Titus.
All right. Okay.
They have this, and I think that a group in Korea, the Seoul National University, they also the church at the Euler insulator, but in the model.
Okay. Yeah. Okay. Yeah. Okay. Cool. Yeah. Thanks for that clarification. Okay. So then it does exist in real experiments. Okay.
Sorry. So you mentioned that this tensor network initially works for this 1D topological systems and does not work for the 2D and 3D. And now you are introducing this Euler insulators. So does it related to that it works for it does not work for strong topological phases? It works for weak or delicate kinds of topological phases? The tensor network.
So it's I think so. Yeah. So yeah. You're right. It might work for weak topological phases because, I mean, the Altland-Zinbauer classification. I mean, the way it's shown, I find a little bit confusing because it always just shows a strong topological label, right? So I mean. So for this multi-band topological classification, also for some cases of the Altland-Zinbauer classification, one uses homotopy groups, right? So actually it's a torus homotopy group, which means that if you classify the Hamiltonians, or basically the maps from the Briorine zone to the Hamiltonian, you have to look at a map from the sphere to the space of Hamiltonians, but also of the lower topological of the lower dimensions to the target space. So what I'm saying is that in the Altland-Zinbauer classification, if you want to look at the different topological phases, you actually have to take the dimension that I showed you. So we can also go back. So I mean, whatever 3 dimensions A3 has the highest label is Z in 3 dimensions for class A3, but then there's also a topological label coming from 1 dimension, and you actually have to, that would be a weak topological index, and you could capture the weak topological indices using tensor network states if they come from 1 dimension. So also in higher dimensions, basically, if you have a sub-label that's just a 1-dimensional label, like the ones that I'm highlighting in red, in higher dimensions, that's something you can still capture. So if the weak topological index comes from 1 dimension, but not from 2 dimensions, then you can capture it with a tensor network state. Is that what you were asking?
Yeah, okay.
Okay, yeah. So tensor network states can capture the 1-dimensional topological labels also if you live in higher dimensions, but they cannot capture higher dimensional topological labels. Right. So, and going back to the Euler system, so they also have a topological label, but it doesn't come from the tenfold classification. It comes from this multi-band classification, and they're also experimentally very relevant, as Zoom just said. And other examples are out of equilibrium systems like trapped ions, which you can see on the left. And they have also been observed in the phonon spectra. So this is the middle one, which was actually done in Cambridge, of monolayer silicates. And in the right bottom corner, you can see a realization of Euler topology in acoustic metamaterials. So where basically, again, the acoustic spectra correspond, or the bands have Euler topology. So they're experimentally very relevant, and this is why so much effort went into classifying these topological phases. Now I want to give a slightly more in-depth introduction into tensor networks. So why are tensor networks so powerful? So why do they capture the ground states of local gapped Hamiltonians? So if we have a Hamiltonian which is local and has an energy gap, and we take its ground state size 0, then it turns out that this ground state fulfills the area law of entanglement. So that means if you take a block A of that system, so I'm just talking about lattice systems here. So you take block A of that system and you trace out the complement A bar, then you obtain a reduced density matrix. And that reduced density matrix, if you calculate its von Neumann entropy, so which is a measure of its entanglement, then this von Neumann entropy is upper bounded by a constant times the number of particles that you have around the circumference of that block A. So these are the blue particles. And this is actually a very strong restriction. So if you took any generic state in Hilbert space and you calculate its entanglement entropy, then this would normally scale like the number of particles or sites that you have in block A. But instead, for the ground states of local gapped Hamiltonians, it only grows like the number of sites that you have around the edge of the system. Of the block A. And that's such a huge restriction that it reduces the quantum many-body problem from something that's exponentially complex to something that's only polynomially complex. So that's what you can see on the right. So in general, the Hilbert space grows exponentially with the number of sites. But since ground states fulfill the area law of entanglement, they live on a polynomially large submanifold of the exponentially large Hilbert space. And this submanifold is exactly what's parameterized by tensor network states. And that's why they can capture the ground states of local gapped Hamiltonians efficiently with only a polynomial overhead in the computational cost. And how are tensor networks constructed? So the simplest tensor network states are matrix product states. And the way of constructing them is starting by maximally entangled virtual particles. So these will disappear in a moment and then create the actual physical wave function, so variation wave function that we're interested in. And the way of doing this is by basically using the most general map that you can come up with from a space of 2 virtual particles on each side to one physical particle, which is the red ones. And the most general map that you can write down is given by a rank 3 tensor. And if you go through that calculation, you obtain what you can see here in the box, a matrix product state. So for matrix product state, if you start with these maximally entangled virtual particles between neighbors and you map them to the physical particles on each side via this map given by the rank 3 tensor, then all the coefficients of the wave functions are given by a trace of a matrix product, and that's why it's called a matrix product state. So here the tensors, the rank 3 tensors AI, alpha, beta are viewed as matrices. So if I fix the upper index I to be a certain value, then it's a matrix, and it's a D by D matrix where D is called the bond dimension. And for each of the coefficients of the wave function, you would have to multiply these matrices with each other to get the coefficients of the wave function, and therefore then the overall wave function. So the upper index I, that's just a physical index. So if you have a spin system that goes from 1 to 2 s plus 1, and the lower indices, this alpha, beta, these are called the virtual indices. And one can make the tensor network more accurate, so get a more accurate representation by increasing the space of these virtual indices, so by increasing the bond dimension D. So tensor network states are a variational ansatz, and one would have to increase this D polynomially in order to keep the accuracy of the approximation fixed. So this is translation invariant matrix product state, so it will look the same on each side, but one can also make the construction non-translation invariant. And what's particularly important is that we never want to actually calculate these exponentially many coefficients Ci1 to Cin, because that would be exponentially complex again. Instead, all the observables that we're interested in with tensor networks, like correlation functions or on-site magnetizations and things like that, can be calculated by just using a few tensors. So all the observables we're interested in will also only require polynomial overhead, polynomial computational cost. We never have to work with anything that's exponentially complex. And a very simple example, especially for the purposes of this talk, is the Kitaev chain. So in one dimension, there's a specific type of tensor network that is given by using Majorana modes. So in each, the virtual particles, they are Majorana fermions. And the physical particles are now constructed by basically combining the Majorana modes together in a natural way to get a physical fermion with the typical anti-commutation relations. And if what I had earlier as maximally entangled states is just a fermion, a virtual fermion in vacuum state by combining the two Majoranas, then the corresponding physical state that we get, which is defined on the red particles, will be the ground state of the Kitaev chain model. So this is a very simple tensor network state which captures the topologically non-trivial phase of class D, which has a Z2 classification. So this is an example of a one-dimensional topological label that's captured by tensor networks. And in higher dimensions, tensor network states can be constructed in the same way. So one starts with virtual maximally entangled pairs between nearest neighbors. So if we're in the square lattice, there will be 4 virtual particles per site. Then one applies a linear map, which is now given by a rank 5 tensor from the 4 virtual particles to the physical particle. And this gives rise to a projected entangled pair state, PEPS, which is normally graphically denoted by these connected lines. And the lines basically tell us how the tensors have to be contracted in order to get the overall wave function. And then based on that, one can check that tensor network states fulfill the area law of entanglement. So one can prove that for tensor networks, the number of bonds that you're cutting is an upper bound on the entanglement. So if I take, like on the left-hand side, a PEPS, and I trace out part of the system such that I'm left with a reduced density matrix on region A, then the entanglement, the von Neumann entropy of the reduced density matrix, is upper bounded by a logarithm of the bond dimension times the number of bonds that you're cutting. And that is proportional to, well, to the number of particles that you have around the boundary of the region A. So tensor networks, and the same for matrix product states on the right-hand side. So there I'm always cutting 2 bonds. And here the entanglement is upper bounded by just a constant, which is the area law in one dimension. And generically, tensor network states also meet this upper bound. So they fulfill the area law of entanglement. Okay, and now I want to actually apply tensor network states to Euler systems. So,
sorry.
yes, yes.
Could you explain why the name projected entangled pair states? Where are you projecting these? So I understood that you had 4 virtual particles,
yeah,
and then you're writing this rank 5 tensor. So what is entangled and where are you projecting this? Why are you calling it PEPS?
Yes. That's a good question. So unfortunately, I don't have the slides for that. So the one thing I would like to say is that the word projection is actually very confusing. I don't like that word, but that's what people use everywhere, because a projector is an operator that squares to itself, but that's not the case. So what you actually have is an operator which maps the virtual particles to the physical particle. So it's actually, we'll have an example of that quite soon. But for now, let me say that you basically start with these maximally entangled pairs. So that's first of all just a pure state of 4 virtual particles per site. And then you would take this state of maximally entangled pairs and apply operators on them, which annihilate the virtual particles. So on each side, it annihilates the virtual particles and creates one physical particle.
I see. Okay, thanks.
Yeah. But the word projection is actually very confusing. Yeah. Okay. So now I want to consider a model of an Euler insulator, but the whole thing can be made more general. So this is a Hamiltonian which is defined on a Kagome lattice with hoppings between different sites. So the first term is, so that's all spinless fermions, and the first term is nearest neighbor hopping between different sites. The second one is next nearest neighbor hopping, and then we also have a next nearest neighbor hopping, but only across the hexagons. So there's no next nearest neighbor hopping through other sites. It's only through the vacancies of the Kagome lattice. And then we have a chemical potential as well. And if that chemical potential is in the energy gap, then the system is topologically non-trivial. It's given by an Euler number with of value 1. And so for the purposes of calculating a tensor network representation, first of all, we set the chemical potential to -2, because then the Hamiltonian actually takes a very simple form. So in that case, if we set mu equals to -2, then the Hamiltonian is just a sum over hexagons. And in each hexagon, we have an all-to-all hopping. So the hexagon is, I mean, you can see them highlighted on the bottom. So these terms acting within the hexagons are hoppings between any side I and side j in the same hexagon, all with amplitude 1. And for that simple case, we can write down a tensor network, as you will see in a moment. So first of all, let me massage that Hamiltonian a bit further. So this all-to-all hopping can be basically written in terms of quasi-particle operators. So this is this A hexagon, where the A hexagon is defined as the combination of annihilation operators acting within the hexagons, all with the same amplitude. So this is the form of the Hamiltonian that we have in that for that specific choice of parameters. And in that case, it follows that a ground state or a ground state, any ground state, is given by the state which is annihilated by all of these quasi-particle operators defined on hexagons. And therefore, the ground state with maximal occupation number can be constructed by starting with the all-occupied states and applying the product of all of the annihilation operators. And it can be checked that this is actually a PEPS. So this is the state that you obtain by starting with virtual fermions, but now not just nearest neighbor, but entangled across hexagons. So for each hexagon, we have 6 virtually virtual fermions, the CJs, which are just in a state that's a linear combination of 0, 1, 1, 1, 1 plus 1, 0, 1, 1, 1, and so on. So where there's just one site that's empty, and you take a translation invariant superposition of that, it's also called a W state. And then we have 2 virtual fermions per site. And again, we map these 2 virtual fermions in each site to a physical fermion. So this is related to the previous question. So this is the operator that you can see on the bottom. The rank 3 tensor is now an operator because we're dealing with fermions. So that operator gets rid of one. So it either gets rid of one fermion on each side. This is the C prime or the C, or it gets rid of both fermions in each site and creates one physical fermion. So one can check that as a result, it's particle number conserving. And this is basically a consistent way of constructing the PEPs such that if you apply this annihilation operator, the A hexagon, the PEPs gets annihilated. Because it has that structure already on the virtual level, because on the virtual level, it's already that superposition of basically a whole translation invariantly moved around the hexagons, which is exactly what's annihilated by the A hexagon. And then this virtual state gets consistently mapped to the physical level. And as a result, one can check, I mean, I won't go through the calculation, that the resulting PEPs is the state which has maximal occupation and is annihilated by all of the A hexagon operators. So this is the PEPs that we can write down. So this model has a specific PEPs ground state, and we can also make this more general. So it's a fairly simple generalization. If one starts with the superposition of the virtual particles now with coefficients in front of them and applies the same on-site linear map to the physical space, then the corresponding Hamiltonian is also has also the PEPs as a ground state, and the Hamiltonian in that case becomes a bit more general. So this is another model Hamiltonian, still all non-interacting, where the hoppings now have prefactors beta I star, beta j, so these are complex parameters. But again, the ground state of this Hamiltonian is given by a PEPs, and if we have to impose PT symmetry to stay in the same class of systems, and if we do that, then beta star I plus 3 is beta I. So this is another class of models, which, or that's basically a generalization of what I showed you earlier, which are all have PEPs as the exact ground states. And if we don't move too far away from the original configuration where all the betas were 1, then we will still be in the same Euler, in the same topological phase, in the Euler phase, and it's still exactly described by a PEPs.
I have a question.
Yes.
Can you go? Yeah. So basically, from the previous slide, the previous one, you use the following idea. You have the Hamiltonian, which is positive definite, and then you find the states that are annihilated by the Hamiltonian.
Yes.
For mu, it's not equal to the values that you choose. How can you prove that the Hamiltonian is the positive definite? Use the same idea.
Yeah. So thank you for this question. This is actually super important, but I forgot to say that. Yeah, the Hamiltonian is positive semi-definite. So it's a sum of projectors, which is really neat. So all of these, I mean, since they're projectors, they have eigenvalues 0 and 1. And the PEPs is the PEPs is a ground state. And it's the ground state which for which all of these projectors give value 0. So you minimize the overall energy of the Hamiltonian by minimizing the energy locally on each hexagon. So it's a frustration-free model, a frustration-free ground state. It satisfies the restriction locally everywhere in the system. But yeah, it's such an important question. So what happens if we switch on the mu? So what actually happens? I'm actually wondering, I might have this. Yeah, okay, I have it here already. So yeah, so here so this is the next section of the talk where I will be talking about the features of these models. If we have mu equals to -2, then the Hamiltonian has this nice form. So if we forget again about the beta parameters. So if all the betas are 1, then the Hamiltonian has this very nice form. It's a sum of projectors. It's positive semi-definite. And the PEPs will be the state with the maximal occupation, which meets this, which is the ground state. And that's very important that it has the maximum occupation, which I could show that in a couple of minutes, but I'm skipping it here to keep things simple. PEPs has the maximum occupation, and therefore it follows that as you switch on the chemical potential, the PEPs will be the unique ground state. So the Hamiltonian is no longer semi-definite, but the PEPs will become the unique ground state because all the ground states which have lower occupation will get energetically penalized as soon as you switch on the chemical potential.
Sorry, I also have a question. So,
yeah.
Could you specify what is the PT symmetry in this Hamiltonian exactly?
Yes, very good question. The PT symmetry in that case means inversion. So basically, if we look at the hexagons, you basically invert around the center of the hexagon. So 180 degrees rotation, it's the same in 2 dimensions. And in that case, I imposed like just pure complex conjugation. So time reversal symmetry is complex conjugation. We could also make this more general and come up with other methods. But in that case, the symmetries that I imposed is if you invert the system and you do complex conjugation, that it goes back to itself.
But this is a symmetry of your state. How does the symmetry translate for the Hamiltonian?
Yeah, good question. So it's the same symmetry. So the Hamiltonian also has to be invariant under, I mean, in that case, applying the inversion operators on both sides and doing the complex conjugation.
Is
Yes.
that it? Invariant and then complex conjugation, right?
Yes.
Okay, and then second question was that, so here the fermions that you consider, these are spinless fermions, right? So is it possible to generalize this ansatz with spinful fermions?
Yeah, very good point. So this, so one just has to be careful about about how exactly one does that. So it is possible to use this ansatz and cook up other topological models. So I mean, the problem for if you first of all introduce spins, then instead of having 2 occupied bands, you will have 4 occupied bands. So it's not protected anymore because 4 occupied bands are topologically trivial for PT symmetry. So one would have to be careful about how one couples the 2 spins. So as Zoom said, there are experimental cases that have spinful fermions and are in the Euler phase, but I don't know if it would still stay a tensor network state. So I don't know. I haven't tried that. Another option is to project it on basically localized fermions, which can't hop anymore. So you have a spin 1/2 system. And in that case, we might end up with a Euler spin liquid. I mean, well, one can cook up that projection and that map, but it's not clear if it's topological. So the answer is we haven't really tried it properly yet, and it's a bit more intricate.
Okay, thank you.
Okay, so to bring everyone back to the same levels. So what I've been doing so far is that I looked at the simple Euler insulator, which has Euler number 1. And we came up with a simple PAPS that is the exact ground, that is one exact ground state of that model. And this is the first case of a non-interacting higher dimensional tensor network state, which has a non-zero topological index. So in that sense, it's a bit similar to the Kitaev chain in 1 dimension. It's sort of the Kitaev chain of Euler insulators, because it's a very simple model and captures a very simple PAPS that captures the model and its ground state exactly. Yes. So, and then something I already alluded to. So if very special features of that Hamiltonian are actually flat bands. So if we look at chemical potential equals to -2, then there are 2 fully degenerate flat bands on the bottom, so which have energy 0, because as Zoom said, it's a semi-definite Hamiltonian. So the minimum energy is 0, and there are lots of eigenstates which have that minimum energy. So they're all the states that are annihilated by the A hexagon operators. And there are actually 2n divided by 3 of these ground states, where n is the number of sites in the system. But as soon as we switch on the chemical potential, so the energy gap is 3. So as soon as we move the chemical potential within that energy gap, so it's larger than -2 and smaller than 1, then the PAPS will become the unique ground state, because all of the eigenstates, the two flat bands, they will basically move down. So mu is within the energy gap. And then the eigenstate which survives is the one with the highest occupation, because chemical potential has -mu, so it has a negative sign. So the eigenstate which has the highest occupation will be the unique ground state, and that's the PAPS. So that was the answer to the previous question. So for as soon as mu is in the energy gap and we have a unique ground state, then this unique ground state is the PAPS. So it describes the case where the 2 degenerate flat bands are fully occupied. Okay, and so something that's relevant from also a bit experimental perspective again is what happens to the quantum metric. So the quantum metric is a measure of the response of the Hamiltonian to perturbations. So it's defined as the trace of over-occupied bands of the derivative of the projection operator on the 2 Lewis Bloch bands. And that trace, that gives rise to the quantum metric. And the determinant of the quantum metric square root is upper bounded by the Euler curvature. And actually what happens in our case, so this is just a mathematical feature, is that this determinant is equal to the Euler curvature, and that's due to the flat bands. So the idea is that if the bands are completely flat, then there is no degree of freedom in the curvature, in this G of k. The curvature is fully determined by the minimum curvature it has to have because of the topological features of the system. And in that case, the quantum volume, which is defined as the integral over this, if this measure, the square root of the determinant, is equal to the integral over the Euler curvature. And since that integral is, 1 divided by 2 pi is exactly the Euler number. So that's why the quantum volume in our case becomes 2 pi. So this is just a mathematical feature of the model we're looking at, and that's entirely due to having flat bands. And the flat bands themselves, they are a result of having the PAPS and the semi-definite Hamiltonian. Okay, and with that, I want to move on to interactions. So the nice thing is of having exact ground states that are simple that we can write down analytically is that we can now use these ground states as...
Okay, I have a question.
Sure.
Okay, can you go to the previous slide?
Yes.
So in band theory, you also know something called the Chern band, not only Euler band, but also Chern band. And interestingly, in terms of Chern band, we have another thing. We have another inequality. So that means the quantum metric is bigger or equal to the square of Berry curvature. So basically now with the Euler curvature and Chern and Berry curvature, we have the upper bound and the lower bound of the determinant of the quantum metric. But in the case of the Chern number, the equality, the lower bound equality happen for the determinant of the quantum metric happen in the ideal flat band.
Yeah.
All flat band have this lower bound, but here you're saying that for Euler curvature, you don't need to have ideal. Like all flat band have this property. Is this correct? Or you have some specific, some special flat band have this?
Yeah. So you say you have an ideal property. Ideal property.
The determinant of the quantum metric have the lower bound.
Yeah.
In terms of the Berry curvature.
Yeah.
And the lower bound only saturate when you have the flat but ideal flat band.
Ideal?
There's some interesting properties that it not all flat band satisfy.
Oh, okay.
But the idea is means the quantum geometry operator annihilate have some null vector. So in this case, the quantum metric has the lower bound. But here you say that the quantum metric also has the upper bound. And the upper satisfied with all flat band.
Yes, that's a very good question. So this is heuristically the case. So for all flat bands in Euler insulators that people have considered, this equality is exactly satisfied, but there's no mathematical proof for that. So that's just an empirical finding. So,
I see.
Yeah. So
in the case of the lower bound for the quantum metric, there's a mathematical proof.
There is a proof.
Yeah, there's proof for lower bound, but here you have it's not yet a proof for the upper bound. Okay, thank you.
Yeah. So this is just what happened in all models that people have considered so far, but it might be just a coincidence. That's not clear. Yeah. Yeah, so this is pretty much intuitive. Okay, so now I want to move on to interacting generalizations. So it's a nice feature of having toy models with exact ground states that we can write down analytically is that we can now use these toy models and the ground states and make them interacting. And so far, there are no examples of interacting Euler insulators, but now we can do this. And it's actually quite simple for PAPS. So if one takes a PAPS and applies a short depth quantum circuit, the new state we get is also PAPS. So that's just a special feature. I mean, a short depth quantum circuit is basically a bunch of unitaries, and one can include these unitaries into the tensors of the tensor network state and end up with a new tensor network state, which is just slightly more complex. So it will have a larger bond dimension, so larger tensors. And the nice thing about quantum circuits or shallow quantum circuits is that by definition, we stay in the same topological phase. So a definition of topological phases is that if we start with any state in a topological phase and we apply a shallow quantum circuit, which also has the same symmetries of the topological phase, then we are still in the same topological phase. So therefore, now if we apply a shallow quantum circuit, which also fulfills PT symmetry on the original PAPS, then we end up with a new PAPS that's in the same topological phase, and that in general will be interacting. And the simplest quantum circuit that one, so first of all, basically the simplest quantum circuit is just a two-layer quantum circuit. It's a very shallow quantum circuit, but it has to be invariant under PT symmetry. And it turns out that if you apply PT symmetry, it swaps the two layers. So it's hard to make sure that PT of U is still equals to U. The main way that I find of ensuring that is by just using diagonal unitaries. So the quantum circuit on both layers just consists of unitaries which are phase matrices, which are diagonal, and therefore they commute with each other. And therefore, if you apply the PT symmetry operator and it swaps the layers, you can swap them back. So it's quite easy to ensure that a quantum circuit consisting of diagonal unitaries is PT invariant. And the simplest example that's non-trivial that one can have is the one that you can see here. So this is where all the gates of the quantum circuit, so in both layers, are given by diagonal unitaries with entries 1, 1, 1, e to the plus or minus I alpha, and alpha is between 0 and pi. And the plus and minus depends on, that's just to ensure that under inversion symmetry, it goes back to itself.
Yeah, I have a question.
Yes.
So you just mentioned that your quantum circuit has two layers.
Yes.
What are these layers corresponding to your earlier Kagome lattice that you had?
Yeah. Yes, I should have drawn
Layers.
a picture. Yeah, I should have drawn a picture. So these are nearest neighbor gates. Second. Oh yeah, here I have the Kagome lattice. So nearest neighbor gates. So you have to imagine, I should have drawn this there between each of the nearest, so like on the triangles, for example, these are all the nearest neighbors that one can have. And we apply one of these gates, one of these U's for each pair of nearest neighbors. That's basically the whole quantum circuit. And it doesn't really depend on the order anyway, because they're all diagonal, they all commute with each other. But these are nearest neighbor gates, which just act on neighboring sites, like all the combinations of neighboring sites. You apply one of these gates, and if you apply plus or minus one, you just have to do it consistently such that it has inversion symmetry.
Okay, but then how do I visualize the layers? I mean, you just have a gate between two nearest neighbors, that's all, right?
Mm-hmm. Yeah. Yeah, between all pairs of nearest neighbors. And you can do that in such a way that you basically have, I should have drawn this. You have one layer of nearest, so you just require two layers. So unfortunately, you didn't see my mouse cursor, but I mean, on each hexagon, you could, I don't know, you might actually, no. In each hexagon, for example, you could put in three nearest neighbor gates on the bottom layer and three nearest neighbor gates on the top layer, for example, if that makes sense.
Oh, okay.
So yeah, you can put in three nearest neighbor gates on each hexagon on the bottom layer, which are non-intersecting, and then three on the top layer, which are non-intersecting. And that's basically, that will be the quantum circuit for one hexagon. And then you can just tile the whole lattice and you should be able to stick to two layers.
So when you are talking about layer, you are talking about a single hexagon, and that's you are dividing it into two parts, like upper layer and lower layer in that sense.
Yeah. But for the entire lattice, so you can tile the entire lattice with nearest neighbor gates, and you just require 2 layers, and then you will have entangled all of the sides with each other. So basically, it looks a bit like you've maybe seen the pictures of variation. What's it called? The resonating valence bond states. Yeah.
Okay.
That's a bit what the picture should look like, but I admit I should have drawn it. So yeah, you can basically tile the whole lattice with nearest neighbor gates, and you just need to tile it once for the lower layer and once for the upper layer, and then you will have entangled all the sides, all the nearest neighbors with each other.
Okay, thank you very much.
Okay, thank you. And the PEPs that you end up with has bond dimension 4. And one can also calculate the new Hamiltonian, which is basically applying the same quantum circuit on the original Hamiltonian. And then since it's a fairly simple quantum circuit, we also end up with fairly simple new Hamiltonian. This Hamiltonian will now have interactions. So the first term that you can see here is the sum over star plaquettes, which is what's highlighted in orange. So there will be, in this star operator, there are, again, hoppings between the sides of the hexagon and then multiplied with the on-site occupation number. So it's a generally interacting Hamiltonian, and the chemical potential stays the same because it's invariant under that transformation. So this is an interacting Hamiltonian. And now we can characterize the entanglement spectrum of that Hamiltonian, which is like a special feature, or the entanglement spectrum normally shows topological features of the systems that you're looking at. And I will skip the technical details, but for tensor network states, one can calculate entanglement spectra quite easily. So there's something called the bulk boundary correspondence, which reduces the complexity of calculating the entanglement spectrum. So the entanglement spectrum itself is by putting the system on a torus that's on the left-hand side and tracing out half of the system. So basically cutting the torus in half. And the reduced density matrix rho A that you obtain is e to the minus h end, where h end is the entanglement Hamiltonian. And we look at the eigenvalues of that entanglement Hamiltonian, which can be done fairly efficiently with tensor network states. And what you can see is the result for the entanglement spectrum with 6 unit cells around the circumference of the cylinder. And K is the quantum many-body number, which is a good quantum number because it's translation invariant around the circumference of the cylinder. And alpha is a parameter that we can use to tune from the non-interacting limits to the most interacting case. So for alpha equals to 0, we have the non-interacting entanglement spectrum, which you can see in the leftmost panel, which has basically 2 zero modes, one at k equals to 0 and one at k equals to pi. And as we switch on the parameter alpha, there will be more entanglement energies coming from the top because the state becomes more non-trivial, has more energies. And these move down as you increase the alpha. But what's happening at the bottom of the spectrum is more important. So you can see that the 0 mode at k equals to 0 persists, whereas the other 0 mode at k equals to pi starts moving up. And as we go all the way to alpha equals to pi, then the lower energy modes, they will have basically all merged together to a single band on top, while the 0 mode at k equals to 0 persists. So we don't have a full explanation of that yet, but this 0 mode at k equals to 0 seems to be a topological feature of the Euler systems that survives as we introduce interactions and actually make the system quite strongly interacting. So this brings me to the summary of my talk. So what I told you is that PEPs can exactly represent the ground state of crystalline topological insulators. So therefore, they also capture the topological labels of these insulators exactly and have the right form of correlations. And I told you that we can really write down concrete examples with a very simple construction and make these more general, both in the non-interacting limit, but also in the interacting case. So we constructed a model Hamiltonian for interacting Euler insulators, for which we know for sure it is in the same topological phase as the non-interacting Euler insulators, because it's related via a shallow quantum circuit, and we can still write down the PEPS wave function exactly and also topologically characterize it. And the outlook would be to consider Euler spin liquids, so where we, for example, get rid of the fermionic degree freedom, and instead we just have a normal spin system, and use a similar construction for these types of systems, but then these will be not related to the non-interacting limit, and they might actually be topologically ordered as well. And on top of that, from an experimental perspective, it would be very interesting to realize these sorts of systems on intermediate scale quantum devices, so on current quantum computers, because the PEPS itself has such a simple construction. It's basically starting with a maximally occupied state and then applying these annihilation operators, which all commute with each other. So the construction of the PEPS itself is already a shallow quantum circuit. And then one can apply another shallow quantum circuit to make the whole thing interacting. So all of that is very amenable to what you can do on current quantum computers, which are basically applications of shallow quantum circuits. And with that, I thank you for your attention.
Was a question?
Sorry, I didn't exactly get what kind of interactions you can introduce to your system with your shallow quantum circuits. Maybe you can illustrate this somehow? What kind of interacting system are you getting? Some Hubbard-like model or?
Yes. Again, this is something I should probably have put into the talk, but I can also show it to you in the paper itself. This is something you can see?
Yes.
Okay, so yeah, that's equation 12. So it does look a bit complicated, but the the new Hamiltonian that you're getting is basically, again, the creation and annihilation operators AI dagger and AJ, but now they're addressed with terms that couple them to the on-site occupation NKN and L. So it's basically you sort of get quasi-particle operators. So instead of having just like genuine fermions hopping between sites I and J, you have them dressed with something that depends on the occupation of the sites surrounding them. So it is not the same as Hubbard. So yeah, I mean, tensor network states tend to have fairly artificial parent Hamiltonians. So it's not the same as a Hubbard model. It's more it's a more like many body Hamiltonian. So in that sense, it's similar to the toric code. I mean, the toric code also has an exact tensor network ground state, but its Hamiltonian is also couples many sites. So it's also many body Hamiltonian.
Thank you.
Yep.
Well, in a sense, the Hubbard model is also a many-body Hamiltonian, right?
Sorry, I used the wrong word. Many body hopping. Yeah. So the Hubbard model is like two-body Hamiltonian, but this will be probably a six-body Hamiltonian or something like that. That's what I mean.
I want to say you have not two-body interactions, but six-body interactions. Is that what you want to say, or some analog of that?
Something like that. Yeah.
Only, so not a sum of two-body, four-body, six-body, but only six-body interactions.
Yes.
Okay.
No, I mean they're. Okay, I haven't looked at into this much detail, but
Should be all of them.
Depend on
All of them.
yeah, I guess you get all of them. Yeah.
Yes.
Yeah, you should get all of them.
may just continue then. And let's say if I want, are there any applications of tensor networks to, let's say, this standard Hubbard model in 2 dimensions, let's say, in order to compute the ground state, or also in 1 dimension where there are exact analytical results? Or is it that you usually have these a bit more different looking Hamiltonian, parent Hamiltonian?
Yeah, very, very good question. So this is a very non-trivial problem that I also tried to tackle in my PhD but failed. The tensor network, so I mean, for non-interacting systems, they're very nice tensor network state, ground state with nice Hamiltonians. And one example is what I showed to you in this talk. If you have interactions, no example has been found yet of a tensor network which just has like a Hubbard type Hamiltonian as a parent Hamiltonian. This is a very non-trivial problem, and it's very hard to satisfy the conditions for that, for the tensor network state to have such a nice Hamiltonian. And also, since I did my PhD 10 years ago, no one else has come up with such a model as far as I'm aware.
Thank you. If I may just ask another question for my self-education. So I to quite get the PT operation leaves the parent Hamiltonian invariant, or is it an anti-symmetry? I mean, does it change the sign of them? What exactly does it do to the Hamiltonian? Keeps it invariant, or the parent Hamiltonian?
Yeah, so it inverts, so it does an inversion, so inverts the sides, like for example around the center of the hexagon, or the entire lattice inverts the sides, and there's a complex conjugation.
Sure, this is the operation, but my question is, what does then happen to the parent Hamiltonian? Does it leave this parent Hamiltonian invariant, or does it change the sign of the?
Yeah, sorry, it keeps it invariant, yes.
Okay, thank you.
Another question, maybe it's sort of related, but since you say that starting with the PEPs, you can then systematically include interactions and then can talk about topology in this context. So I was wondering whether this type of lattice Laughlin type ansatz states that one can obtain using conformal field theory, in a sense, whether this can be connected to these PEPs in some way, or is there a theorem that says that they cannot be connected?
Yeah, very good questions. So Laughlin type wave functions have been written down in terms of tensor network states, but then they have an infinite bond dimension. So it's a bit artificial. So because you would, I mean, the D is basically the number of parameters that you have in the system, and the range of the indices of these tensors, and you basically have to take the D to infinity. I mean, you can still write down something that's fairly compact in terms of the conformal field theory, and you can formally write it as a tensor network state, but it wouldn't be like a conventional tensor network state because the tensors would suddenly be infinitely large. So this is what has been done with tensor network states, but for chiral systems, they suffer the problem with the edge modes. So in the non-interacting limit, tensor network states cannot exactly represent chiral topological systems, because it seems like the edge modes, which have long-range decaying correlations, also give rise to long-range decaying correlations in the bulk of the tensor network approximation. So what we've seen in all studies so far is that if you do numerics with tensor network, you, for example, get the Chern number right, or you might also get a fractional topological insulator right in terms of topological features. But at the same time, the bulk correlations of tensor network ansatz will be algebraically decaying as well, which they shouldn't be. And that's the problem tensor network states have with chiral topological systems, or with higher dimensional topological indices in general. But in terms of, so in terms of exact ansatzes, for example, you can write a Laughlin wave function as a neural network exactly, but not as a tensor, because neural networks have these long-range links between the different neurons. But then, since tensor networks are local, they're struggling with this sort of competition between having something that's long range in the bulk and something that should have short range correlations. Sorry, long range at the boundary and short range correlations in the bulk. So tensor networks cannot reproduce that.
Okay, thanks.
it looks quite strange question, but just curiously, is it possible to count in the effect of some phonon or thermal effect on the ground state of the tensor network? I'm asking this question because you talked about its application on the quantum technology. So I wonder if it is possible to calculate or induce some decrease time or dissipations from environment using the tensor network.
Let's see. Yeah, so one can also describe open systems with tensor networks, and I think this has been done quite successfully. At least I saw quite successful papers on that in the last couple of years. But I guess if we talk about quantum computers, the goal would be actually to have as few decoherence as possible, such that one can represent the ground state of, for example, this Euler model with a quantum computer, and then you could use a tensor network, for example, to describe what happens on the actual quantum computer by viewing it as an open system. I mean, that's something you could do. That's your question. So yeah, so in principle, one can also capture open systems with tensor network states. But yeah, for quantum computing realization, one would probably want to keep the error rates as low as possible, such that we can actually see the features of this Euler insulator on a quantum computer.
If there's no more questions, let's thank the speaker again.
Thank you.
Thank you very much.